Okay, welcome everyone to this lecture. So in this lecture, we'll be covering kinematics in two dimensions. So this basically kinematics in 2D, which is two dimension. Okay, I am going to explain right now what these kinematics in 2D mean. So in order for you to actually follow this lecture, you should have watched the video on units and conversions. You should have watched the videos on vectors, especially those on vectors. And then also you should have watched a video on kinematics in 1D, or at least you should have some background knowledge on all of those topics. And then so you don't have to watch my videos, otherwise also some background knowledge on those topics is still also fine. And if you like this video, before I start, if you like this video, you enjoy this content, such content, you want us to make such content, please do support the channel, subscribe to the channel, or just like our videos, share our videos as well. Subscribe and like, actually, not all, and like, and share our videos as well with your friends on social media, wherever you can share this. As long as you're in high school, you not this one is not for high school. This topic is for university. So this one is for university students, and then they can actually just look at this topic and share it. And then also you click the notification bell as well. All right. So you remember we did motion where we had a situation whereby we had something is moving from the x, right, in the x direction. So, and then we also had motion whereby something was just moving in the y direction, like when you throw in a ball and then it goes up and then comes down, it's just moving in the y direction. Okay, and then we had equations of motions for this. We had equations of motions for this. So for instance, this one would say v1, if I had v0 here and I had v1, I'll say v1 is equals to v0 plus a delta t, and then means that it's accelerating in that direction. Could use like v1 squared is v0 squared plus 2a delta x. We could use like delta x is equals to v0 delta t plus half a delta t. We could use like delta x is going to be equals to half v1 plus v0, and then we said this is delta t. For this one, we could say v1 is equals to v0 plus half plus 80 plus 8 delta t, sorry, not half. And this one, we could say v1 squared is v0 squared plus 2a, but then we say delta y. This one we could say is delta y because we are interested in the y direction. And then this is v0 delta t plus half a delta t squared. So this one is fine. Then here we could say delta y is half v1 plus v0, and then this is going to be delta that. Okay, so basically this is what we used when this was 1D. Everything here was one dimension, was kinematics in one dimension. Whether something was moving in the x or something is moving in the y. Now the issue starts when something is moving not in the x, not in the y, but something like this. And now it is covering distance delta x, still have acceleration maybe in that direction, right? And maybe I have like v0 here, and then maybe like I have v1 here, and then but then this is at an angle. I mean, let me say like it's at 30 degrees, and then what do I do? And then how do I actually work this one out, right? If I want the x and the y directions, how would I actually work it out? So this one is where the problem starts. Okay, so I'm just going to be discussing that so that it helps you actually solve problems that are in this reference, in this type of situations. Okay, the first topic that I would actually look into is displacement in two dimension displacement, and then I'm going to do example. Everything I'm going to discuss, do example, discuss, do example. All right, let's just do displacement. All right, now let me say, for instance, I have an object that moves from here and then ends up here. So I can write the displacement vector like this. If I know theta, there's my theta. There's going to be an x direction here. So this will be my delta x vector. There's going to be a y direction here. This will be my delta y vector. I can find the x and the y component of that. This is going to be equals to the displacement vector in the x direction and displacement vector in the y direction. Now from this we know from Pythagoras we can actually find the magnitude of delta x, which is just going to be delta x squared plus delta y squared. I can find the angle theta by just taking delta y over delta x. Again, go and watch the video on vectors to understand what I'm doing. All right, so I could find that. Let's just do a simple example. And before we do the example, I can actually also find delta x. Delta x will be given by delta s. If I know delta s, cos of theta. Okay, and then my delta y will be given by delta s, sine of theta. So I could actually even find the components if I know delta s. So I could either use this method depending on what information I'm given, or I could also use this method, just depends on what information do I have. Okay, if I'm given delta x, they want that and that, I use that. If I'm given delta, I'm not given delta s, but I have delta x and y, I can find delta s using this method one. This method one, and then this is method two. All right. So it just depends on the information that you are given. So let's just look at an example. Right. The first example, maybe I'm just saying, okay, fine. I'm just going to give you the vector delta s, and let me just say this vector is 8 meters. Then I want you to find the the displacement in the x and the displacement in the y. That's basically what I want you to find. Then I'm telling you that this is 32 degrees. So how you could do that is you could say, well, delta x is going to be equals to delta s cos of theta, whatever theta is, and this is going to be equals to 8 cos of 32 degrees. Okay, and then that is basically going to be how many meters? This is going to be 6.8 meters. Okay, I can find delta y, and then delta y is going to be delta s sine of theta, which is 8 sine of 32 degrees, and this is basically going to be equals to 4.2 meters. All right. So this is basically how I could find it. And then in a situation whereby I'm given the x and the y component, I can find it as well. Then I'm going to give you 3 situations. So let me say, for instance, I have an object that travels 5 meters in that direction, and then turns and then travels 7 meters in that direction. Okay, they want me to find this displacement here. So what I could do is I could say, well, delta x is going to be equals to 5 squared plus 7 squared, whatever is on the x, whatever is on the y. This is delta x, this is delta y. All right, and then I can find that. So that is 8.6. Okay, if I want the direction, I'll say tan theta. Take whatever is on the y divided by whatever is on the x. Right, again, if you don't understand this, go and watch the video on vectors, and then there's my theta. Then everything here is just going to be very easy for you to understand. All right, and then this is going to be equals to 54.5 degrees. All right, again, you can write this and say that my delta s is going to be equals to 8.6 meters, 54.5 degrees in the positive x-axis. So you already know this. Remember, I'm assuming that you have done vectors and then you've done equations of motion. If you haven't, please go and watch my videos first and then come back and then actually do this section. All right, so that you understand, because I'm going to be moving in such a way that you know this, you know this, you know this. I'm only teaching you, showing you how you can actually put everything together. That's basically what I'm focusing on this video. Okay, so what about if I have a situation like this? A person basically goes 5 meters in this direction. Let's call it vector A. Then they go 5 meters in that direction. Let's call it vector B. 7 meters. All right, let's not put the vectors. And then they also go that direction. And then maybe let's just say this is vector C, and this is 8 meters. Okay, so how will I find my displacement vector? Remember, your displacement vector is always from the start to the end. Okay, and then there's your displacement vector. If you could draw a straight line, it would look like that. Okay, there's your displacement vector, delta s. So you can see here delta s is going to be equals to vector A plus vector B plus vector C. That's basically what your delta S is going to be. And then this is going to be equals to what is vector A? Vector A, if you look at it, because you could put Cartesian planes here, you could put Cartesian plane here, you could put a Cartesian plane here. So this is in the X. And remember what I said in vectors, you could move this vector here as well. You could move that. So you can actually do it. So it would look something like this: vector A, vector C, and then vector B, right? So this could be vector A, vector C, sorry, and then this could be vector B, right? Then your displacement is still going to look the same. It's going to look like that. This is the same. Then your theta is going to be here. All right, so I could rearrange and put everything that is on the X, but let's fine, let me not do it here. This is going to be 5 in the X direction. This is going to be 7 in the Y direction. And then this is going to be 8 in the X direction. And then when I put the X's together, this is 5 in the X plus 8 in the X and then plus 7 in the Y. So this is going to be 13 in the X direction plus 7 in the Y direction. All right, so this is how your displacement vector would look like in component form. If you want the magnitude of that, it's just going to be whatever is on the X, which is 13 squared, whatever is on the Y, which is 7 squared, and then this is going to be equals to 13 squared plus 7 squared. This is 14.8. Okay, if I wanted theta, I would just say 10 of theta is going to be whatever is on the X, which is 7, whatever is on the Y, which is that. Then my theta is going to be equals to, okay, so this is going to be equals to 28.3 degrees. That's basically what my theta is going to be. All right, so these are different ways you can actually find this. All right, so let's move to another component. All right, so another component is going to be velocity. So how do we deal with this quantity velocity in 2D? All right, so again, I mean, this is a situation whereby, let me say you have a constant velocity v and it's moving at an angle theta. All right, again, this one would have vx, it would have vy. Okay, so I could find a vector v is going to be vx plus vy. That's my vector v. Okay, could find the magnitude of v, which is going to be the square root of vx squared plus vy squared. That's basically the magnitude of that. Then I could also find vx, which is going to be equals to v cos of theta. Could find vy, which is going to be v sine of theta. Remember, this depends on your geometry, on your geometry, right? For instance, if I have that vector, let me just have it in the same direction. If I have it, but then my theta is here, it's not going to be the same. If my theta is here, then my vx is going to be equals to v sine of theta. Why? Because vx, this would be vy, and then this would be vx. You can see that my vx is opposite the angle theta. Right? So don't just claim this. This is true for if you have the first quadrant and theta. It just depends where theta is. Even here, it's still the first quadrant, but theta is there. So it just depends. So don't claim it. Just make sure that you understand what's happening, and that's very important. All right, so an example on this one, it would be something like this. Okay, I'm going to have the same approach. I'm going to say, well, what happens if I have a vector v and that vector v is 30 meters per second and it's moving at an angle of, let's keep it at 32 again. All right, so we all agree by now that there's going to be vx here, and then there's going to be vy here. Okay, I could find this vx and vy. Vx would be v cos, in this case, of theta, which is v, which is 30, cos of 32 degrees, and then that is going to be equals to, that is going to be 25.4 meters per second. Then my Vy is going to be V sine, no, not cos, sine of theta, which is 30, sine of theta of 32 degrees. And that is basically 15.9 meters per second, right? So that is my Vx and that is my. What if, for instance, I said to you, no, for instance, I say, no, it's fine. There's an object that actually covers 5 meters that way, same 5 meters we use. So delta x is going to be 5 meters. Then they cover it in 20 seconds. Then afterwards, they turn north, and then they basically cover 7 meters, same 7 meters that we had, 7 meters. What am I doing? Yeah, delta y, I'm right. It's going to be 7 meters. Okay, and again they take maybe like another 20 seconds, so they cover that distance 20 seconds, right? So the question is, what is the final, what is the velocity? All right, so we just want this velocity. What velocity would they travel? I mean, definitely do they travel that velocity? That's what we're looking for. All right, so we're looking for that velocity. So what you could do is just find the velocity here in the x, what velocity we're traveling here in the x with. All right, and that velocity is Vx. That is going to be delta x over that time. So they took 20 seconds to get there. So that will be 20 seconds. Sorry, not 20 yet. That will be that over time, which is going to be 5 over 20, which is a quarter, which is 0.25 meters per second. All right. Then let me say they covered 7 meters in 20 seconds going up. So you could find your Vy. And then your Vy is going to be equals to delta y over the time that they took to move up. And then that becomes 7 over 20. Okay, so that's basically 0.35 meters per second. All right. Okay, let's just put it 50. Let's make it 50. Let's make it 70 meters, and then this is going to be 50. This is going to be 50. Because I just want nice values. Okay, if I make those 50, this is going to be 2.5, and then this is going to be 3.5. So this is going to be 2.5, and then this is going to be 3.5, just to have nice values. All right, so that's my Vx, and then that's my Vy. All right, so the velocity V will be given by Vx plus Vy. So which means that if I wanted that velocity V, it's going to be equals to, the magnitude will be the square root of Vx squared plus Vy squared, which is the square root of 2.5 squared plus 3.5 squared, and that is going to be equals to 2.5 squared plus 3.5 squared. That's basically 18.5 meters per second. Okay, so that's basically what I get for V. All right, and then in terms of the direction, tan of theta. All right, so tan of theta would be whatever's on the y, which is 3.5, whatever's on the x, which is 2.5, and then basically I can get theta from there, which theta is going to be equals to. So I get 54.5, sorry, which is the same as the displacement vector that I got, the direction of the displacement vector that I got. And that's basically how you could actually deal with velocity vectors. Now let's get to this one that is normally not so nice for a lot of students, so I have to do a lot of explaining here, and that is the acceleration vector. All right, so acceleration is not a very easy concept. I've gathered from my experience. that students actually tend to understand very well. They sort of get it, but somehow they don't get it. So you always have to explain a lot, and that is why even on my video, the previous video, I spent some time, explaining these concepts, because it's very important that you understand them from the fundamental level first. So if I have an object that is moving maybe from point A to point B, but it is accelerating in that direction. So it means that I have acceleration in that direction. So my acceleration vector is pointing in that direction. If you look at this acceleration vector is made up of AX. There's your AX here. And then you have AY, and then there's your AY here. So you have these two. Then there's an angle of theta there. All right. So the acceleration is basically made up of AX plus AY. Okay. So which means that if you want the magnitude of acceleration, you can't find it. It's just going to be AX squared plus AY squared. Also, if you want the direction of that acceleration, you can find it as well, which is just going to be AY over AX. So this is all good and well, and it means that I can actually also find this component, the AX component, which is going to be A cos of theta. Can find AY, which is a sine of theta. Again, remember, it just depends on your orientation and where your angle is. Make sure you always remember this thing. So this is good and well. We can even come up with simple examples on this one. All right. So let me say, for instance, I give you the acceleration vector. There's the acceleration vector, and I'm telling you that my acceleration is 3.2. Then I want you to find AX, and I want you to find AY, and I'm telling you this is traveling at 28 degrees. This is at 28 degrees. All right, so you could find either of them. You could say AX is going to be A cos of theta, because it's going to be, your AX is going to be here. There's my AX. Then my AY is going to be opposite the angle. So this is my AY, and then this is my AX, basically. All right, so that is fine. That is good and well. So that is 3.2 cos of 28 degrees. And that is basically 2.8 meters per second squared. Then also you could also try to find AY. AY is A sine of theta, which is 3.2 sine of 28 degrees. And basically that is 1.5 meters per second. Now I'm already, oh, there's the square. I thought I forgot the square. Sometimes I forget the square when I'm writing acceleration. So that's basically it. I mean, this is easy. You could also find it. Let me say, for instance, you were given the acceleration vector in that direction, and maybe let's say the acceleration here is AX is 2 meters per second squared, and then you're given the acceleration here, which is going to be AY, and let's just say AY is 3.5 meters per second squared. Then you are asked to find A. All right, maybe they say find A for us. All right, so what you could do, you could say, well, the magnitude of A, remember, is going to be the sum of AX plus AY. So which means that the magnitude of A will be the square root of AX, which is 2 squared plus 3.5 squared. Okay, so which means that A is going to be equals to 2 squared plus 3.5 squared. And that is basically 4 meters per second squared. Okay, and then I can find the direction of that. My direction of that is 10 of theta, and then 10 of theta is going to be whatever is on the y, which is 3.5, take it as positive over 2. All right, so which means that my theta is going to be equals to, and my theta is going to be somewhere here. Again, if you watch vectors, this is easy if you watch vectors. If you haven't, you are confused, what am I doing? So if you are confused, go back to vectors. Okay, so this is going to be, theta is going to be equals to 6.3 degrees. All right, then you also know how to actually state it as a final answer from your vector videos. Okay, all right. So from here, let's have a situation that generally confuses students. Okay, now this situation is like this. Let me say, for instance, I have a car or someone, whatever, traveling that way. Maybe let's just say their velocity Vx, they are traveling that way with a velocity of 30 meters per second. And they cover and they take 20 seconds to get there. Then they turn. They go up, and now they're traveling velocity Vy, which is still 30 seconds. So let's just assume the 10 was somehow, we don't take into account the time that they slowed down to 10. So let's just assume it happened very fast. They put 10 like that, right? So they never changed the speeds. Everywhere the speed was the same. So they could just do it like that with the same speed. All right. And this is 20 seconds. All right. Now the question is, what is the acceleration vector? Now this is where students get confused, because what the students say is, well, no, I mean, the change in v is going to be equals to 0 because this is going to be equals to 30 minus 30. All right, that is not true, right? Or to say, no, the speed is constant, so it's going to be 0 because if the speed is constant, the acceleration is constant. That is also not true. Remember how you get acceleration. You get acceleration by saying that the acceleration vector is given by the change in velocity over the time period, over the change in time period. Basically, that's what you have. All right. So you have to find out, is there a change in velocity vector? If there's a change in velocity, then there is acceleration. Let's look at this problem. If you look at this problem, what is change in velocity? The change in velocity is always the final velocity minus the initial velocity. It's always the case. So in this problem, change in velocity is going to be the final, which is Vy, that's the final, minus the initial, which is Vx. It started at Vx. So let's draw these vectors. Do I have that vector? All right, now remember what I said in vectors. I said this is the same as that. So you are basically adding minus Vx. That's basically what you're doing. All right, this is basically how it looks like. And then if you do it like this, what you're then doing is, what is Vy? Vy is going up. There's Vy. Vy is going up. What is minus Vx? Minus Vx is going that way. Go and watch my vector videos when subtracting vectors. I did explain this. There's my minus Vx. So you can see that my change in Vx is from here to here because it is a change in velocity vector. There's my change in V. And there's my theta. You could put your theta here and then describe it if you want. Or you could put your theta here. It just depends. We can draw it differently. But basically, this is how it looks like, which means that I am going to have the acceleration vector because the direction has changed, and therefore it means that I have a change in velocity, in velocity vector, and then therefore I have the acceleration. And the acceleration is always going to be in the direction of change in v, which means that the acceleration is also going to be in this direction as well. Right? Whatever the direction of change in v is, that's the direction of the acceleration vector. All right. So let's just do this example. I think we'll have two approaches on it. Let me just approach it two approaches basically. All right. So the first approach is sorry, that I'm going to do is, we already know that there's going to be those velocities. So I could find the acceleration when it was going that way. All right. So I could find the acceleration when it's going in these different ways. All right. So that's fine. That's good. Okay. So in order for me to find that, what I then do is this. I could say, well, this acceleration vector is going to be changing v over changing time. And the time that I have to take now, I have to take the time that I had that acceleration vector, basically. All right. And what is that? That this change in v is going to be equals to Vy, all right, minus Vx. over the change in time, over the change in time. And this is going to be equals to Vy over change in time minus Vx over change in time. Okay, I can rearrange this and I say this is minus Vx over change in time plus Vy over change in time, right? And then if you look at this is the same as you have the minus, but then velocity over time is basically acceleration, but is in the x direction. Then this is going to be acceleration in the y direction. This is for this problem, not for every problem. For this problem, this is how this problem basically reduces to. Because if the original vector was facing that way, then to change this basically orientation here. So this is basically going to work. For this problem, this is going to work. All right. So what is that acceleration ax? So it means that my ax in this case is just going to be vx over this. And what is that? I mean, that is 30 over the total time. I don't take the 20 seconds because I'm looking at the acceleration from when it was moving from A to B. I'm looking for that acceleration. All right. So I have to take the total time because the way I did it was I took the total time and there's the total time. So I have to use the total time, which is going to be 40. And basically this is going to be 0.75 meters per second. What is my AY? My AY is also going to be equals to VY over 40. So Vy is 30 again, and then you divide by 40, which is the total time. The total time is 20 seconds plus 20 seconds. Again, this is 0.75 meters per second. Now let's put this. This is going to be minus 0.75 in the x direction plus 0.75 in the y direction, which works out because it's 0.75 there. This is the ax, which is minus 0.75 in the x. And then I have the positive, which is like that, and then this is ay, which is 0.75 in the y direction. Now if you look at my vector, there's my acceleration vector, there's my a vector, which is the same as this one, right? The same as this one. So you could see it's still the same, and I could put theta here if I want. All right, so instead of putting theta here, I'm going to put theta here. So you have to be very careful here and understand the basic definitions of things because you may confuse things here and get confused and then just mess things up. All right. So if I want my ay here, my a is just going to be the square root of ax squared plus ay squared, and that is basically 0.75 squared plus 0.75 squared. So this basically becomes 1.1 meters per second squared basically. So that's basically what I have. Okay, that's my acceleration vector. If I wanted to find the direction for this, could find the direction, you just say tan of theta is going to be ay over ax, which is 0.75 over 0.75, which is 1. All right, and then which means that theta is going to be 45 degrees. Basically, that's what it is. Right, and then you already know how to state it. Now let's use method 2. Method 2, how can we find it using method 2? All right, so we want to use the second method. All right, now the second method, remember what you have Vx moving at a constant velocity of 30 meters per second in 20 seconds, and then tens moves Vy 30 meters per second in 20 seconds. All right, then what we said was you have to find the acceleration is going to be equals to delta V over delta t. So you just have to find the delta V vector first and then put that and then you calculate it. And then we're going to use that method. All right, so what is my delta V? So I have my Vy like that, I have my Vx like that, Vy, Vx, there's my minus Vx, there's my Vy, because remember, delta V is going to be Vy minus Vx. Okay, so which means that my change in velocity vector is going to be this one. So let me find that change in velocity vector. So my change in velocity vector is going to be equals to 30 in the y direction minus 30 in the x direction. So it is the same as minus 30 in the x direction plus 30 in the y direction. I mean, this is the same. So there's my delta V. So find the magnitude of this delta V. Find the magnitude of delta V, which is 30 squared plus 30 squared. And that is going to be equals to 42.4. This is going to be equals to 42.4. That's the magnitude. And the direction is going to be equals to the direction of delta V, tan of theta. It's going to be 30 over 30, which is equals to 1, which means that theta is 45. So it's the same as the acceleration vector. Sorry about that. My voice, I don't know what's happening with it. I have this problem. All right. So that's what I basically have. So now let me find the acceleration vector. The acceleration vector will be given by delta change in that over change in velocity over the change in time. I've already found the change in velocity, and it's going to be the vector. All right, I already know the direction, I already know the magnitude. So it's going to be 42.4 over 40. All right, and the acceleration vector is going to be, and that's 1.06. 1.06. This is approximately the same as 1.1. Right, so because of the rounding off, and that is why we have a different answers. So you got 1.14 before, now you get 1.06. It's because of the rounding off. Okay, and then this is in meters per second squared. And you could find the x and the y. I mean, once you have this, it's very easy to find the x and the y. You already have the acceleration, and the direction of the acceleration is going to be the same as the displacement vector. So if change in v, not the displacement vector, if change in v is in this direction, then a is also in that direction. And so we found that this is going to be equals to, this is going to be 45 degrees. This is also going to be 45 degrees. All right. So basically that's what you're going to have. So you can see that I can actually find the acceleration in two ways, and to find the components, you can find components easily using that. Okay. So it's going to be slightly different if you're using that. So let's see. So if I say I'm going to use this 1.06, so if I wanted the components, I could say AX is A cos of theta, which is going to be A 1.06 cos of 45 degrees, and that's going to be equals to 1.06 cos of 45 degrees. This is 0.75, 0.75 meters per second squared. And then also if you want AY is the same, but then it's just that it's going to be the sine of theta. All right. And then this is going to be, let's see if it's going to be the same. So I have AY, and then I have AX like this. And then there's my theta. So the way I calculated theta is I found theta like this. So this becomes my AX minus like that, and then this becomes my AY. So you have to be very careful about that. That's how you found your theta, because you said y over x. So you must remember, so it's above the negative x-axis basically. So this becomes A here. This becomes A here, and then this becomes AX here. Then this becomes AY here. Right? Even if you put VX, VY is still the same. All right. So there's my theta. There's my 45. So that's why I could do it like that. So that's fine. All right. So this is 1.06 sine of 45 degrees. It's just gonna be 0.75 meters per second squared. If you use 1.1, I think you're gonna get something else. If you use 1.1, you're going to get 0.78. So if you use 1.1 instead of 1.06, you're going to get 0.78. All right, so it's fine. That's just rounding off. Those are rounding off basically issues or errors, right? Then that truncating, so it affects your precision. All right, so this is what I wanted to explain with acceleration, and I think this is fine. And then now we can actually move to equations of motions, which is something also that confuses students. All right, so there's a lot that we have to cover here. on equations of motion, and then I'm going to do one example that is going to clarify most of the things and as to how you can actually work it out. Okay, let me say you have an object. It moves from point A, then it moves to point B. Let me say it had an initial velocity of v0, and then it has a final velocity of v1 that is higher. That's why it's longer. So it means that I can actually draw that my object actually, if you assume that the object moves in a straight line, if my object moves in the straight line like this, it's going to get there. So it covers the distance of delta s, it takes the time of delta t, and since the speed is going to change, there's going to be acceleration in that direction. It's going to be acceleration in the direction of v1 and v2 and v0 and v0 and v1. Okay, so that's what I have. Right now, the most important thing to realize is that if you look at the vector v0, it has the x component and the y component. So v0y, v0x. So I could actually describe this as it was moving there, it covered this distance in the x and it covered that distance in the y. So this is the distance it covered in the y, this is the distance it covered in the x. So when it was here, the initial velocity in the x direction, it was the initial velocity in the x direction. Then here, there's going to be the final velocity in the x direction. Here, there's an initial velocity in the y direction, which is the same point as here. Then here, there's going to be the final velocity in the y direction. So which means that there's going to be acceleration in the x direction and there's going to be acceleration in the y direction. Right? So if I know theta here, since it's traveling in the same direction, if this is theta here, therefore it means that this is going to be theta as well. Okay, so I can find v0x. V0x to be given by v0 cos of theta. v0y will be given by v0 sine of theta. I can do the same for the v1 vector, which is this velocity 1 vector. It's also theta. So this is v1. And then this is v1y and v1x. Okay, so I could find that. I could say, well, then my v1x is going to be v1 cos of theta. My v1y is going to be vy sine of theta. That's basically what I'm going to have. All right, so I can have that, and then you can actually see here that there's also this time. So now let's explain what happens with time before I write the equations of motions for this case. All right, so what actually happens with time? Okay, so you have your object that is moving like that, and let me just say it takes some time to get there. All right, let's just say it takes some time to get there. Let's just say it takes 20 seconds to get there. To move from point A to point B, it takes 20 seconds. So when it's somewhere here, which is like 5 seconds, then how much distance is covered in the x? It is covered this distance in the x and that distance in the y. In how long? In 5 seconds. So it is here, that is distance covered in the y, this is distance covered in 5 seconds. So which means that this distance delta x here is also covered in 5 seconds. This distance delta y here is covered in 5 seconds. When it's here, let me just say here is like 15 seconds. It has now covered this distance x. It has now covered this distance y. How long did it take to cover x? How long did it take to cover y? It took 15 seconds to cover x. It also took 15 seconds to cover y. So you don't add the 15 seconds. You don't say it took 15 seconds and then 15 seconds. No. In 15 seconds, it covered this distance x, it covered this distance y. So it covers x and y at the same time. As it's moving in the x, it's also moving in the y at the same time. It's not like it covers x first and then changes and then goes to y. No. as it is moving in the x, it is also covering the y. So which means that if it took 20 seconds to move from point A to point B, you can think of it like this. It is, I'm not sure if you can see, it is also 20 seconds. It is also 20 seconds to get here. That's my delta x. So my delta x is 20 seconds. So this is also point A to point B. It is also 20 seconds to move from here to here. This is also point A and point B. So it covered that distance, took 15 seconds. It took 15 seconds. It's also doing it 20 seconds. Sorry, it's 20 seconds and also 20 seconds. So it covers this distance same time. So when it was here, the y was 0, the x was 0. When it was here, the y maybe was 20, and then the x maybe was something else, right? The y was something else, then the x was something else. But then it is covering that distance at the same time. Hopefully you guys understand that point. All right. So when it's here, the distance is at 0 seconds is here. At 5 seconds is here. How much distance is it covered at 5? It has covered this y, it has covered this x. At 15 seconds, it is here. How much x has it covered? It has covered this x, it has covered this y. At 20 seconds, it is here. How much x? It has covered that x, it has covered that y. Right? So it's covering it at the same time. So as it is moving in this line, it is covering x and y at the same time. All right. That is why we say that, therefore, the displacement vector has the x component and it has the y component. And that is very important. And it takes the same time to cover that. All right. Okay. So what it means that at 0 it was here. At 5 seconds it was here. At 15 seconds it was here. And then at 20 seconds it was here. Here at 0 seconds it was here. At 5 seconds it was here. At 15 seconds it was here. At 20 seconds it was here in the x. And when you combine the two, you basically get that displacement vector. So hopefully I'm not confusing you guys. All right. And this is very important that you understand that. All right. Another thing is, since my v1, I mean, I have velocity 1 here. I have velocity 2 here. So you can see that I have my v0 here. Sorry, v0 and v1, not v1 and v2. So it means that I am moving in that direction, increasing my speed. So it means that my acceleration also is moving in that direction. So also my acceleration vector A has an x component ax, and it has a y component ay. So meaning that as it is accelerating in that direction, it is accelerating in the x and the y at the same time. Okay. So as you are moving, you are having the x component, the y component, you're having the x component, the y component. Everything is happening at the same time. It's not like you go to x first and then you turn and then you go up. No. It's not like that. You are covering x and y as you move along. You are covering it at the same time. So hopefully you guys understand that part. If you still don't understand that part, try just leave a comment, and then maybe I'll find ways maybe to explain it, and then maybe I can just do a separate video that is going to be in detail. All right. If you don't understand this part, just leave a comment, and then I will know that you don't understand this part. Okay, so let's summarize how we can actually deal with these types of scenarios. Okay, so if I have, there's the object is moving from A to B. I'm just redrawing everything, and then it has a speed of v0 here, it has a speed of v1 here. Okay, and then it's going to accelerate in that direction and is covering a distance of delta s. Okay, so it's going to accelerate and move in that direction. All right, so what we said was there's going to be the x component of the motion, where it's going to cover delta x, is going to accelerate at ax, and then it's going to be speed v0x and v1x there. And then it's going to go up like this, and then we're going to have v0y, and then we're going to have v1y. And then the acceleration will be ay, and then it's going to cover the distance ay as well. All right, so that's what we have. So how do you write equations of motions like this? All right, so if you are using the path A and B, right? If you're using this blue path, your equations of motions are going to look like this. You're going to say, well, my v1, which is v final, is going to be v0 plus the acceleration, which is this acceleration, and then my delta time, whatever time that you take to move from point A to point B. Okay, so the time is going to be the same for all of them. And then you can also say v1 squared is going to be v0 squared plus 2a delta s, because you are using the path delta s. Could find the delta s path also and say v0 delta t plus half a delta t squared. Could do that. Could also say delta s is going to be equals to v0 plus v1, half of that, forgot half, delta t. So this is if you're using the path a and b, a to b. So that's what you're using, a to b. All right. What about the x component? What is happening in the x? What is happening in the x? So in the delta x, what is happening? v1 x is equals to v0x. So you must use everything that is on the x now. And then you say the acceleration in the x direction. The time is the same. Doesn't matter which path you take, the time is the same. Then this is v1x squared, v0x squared plus 2ax, and the distance is delta x because we are only considering how long it will take to cover, and while accelerating, while how long it will take you to cover this distance at that time, in that particular time, and accelerating at that particular acceleration. We could also find delta x, which is going to be v0x. Delta time is going to be the same, plus half a of x t squared. Then you could also find delta x, and that is going to be given by half v0x plus v1x. It doesn't matter whether you start with v1 or v0, it doesn't matter, and then delta t. Okay, what about the y? All right, the y, let's put it somewhere here. Can I put it somewhere here? Feels like I can't, so I'm going to write it somewhere here. All right, so the delta y for in the y direction is going to be vy1 1y v0y plus ay delta y. Sorry, not delta y, delta t. Delta t. This is going to be v1 y squared v0y, not 1, squared plus 2ay delta y. Another one, you could find delta y, which is going to be equals to v0y. So you have to be very careful what direction you consider, what velocity you consider it. And then this is going to be delta t is the same. You're taking the same time to cover that distance, and then t squared. Right, so this can be confusing at times, I know, but then just make sure that you don't make these mistakes. Then this is y1. It doesn't matter whether I start with 0, v0y or v1y, it doesn't matter because I'm adding. So all right, and then basically, and then this is delta t. All right, so these are the 4 equations that you can use in the y direction. All right, in the y direction. In the x direction, you could use these ones. In the y direction, you could use these ones. Let me see if I can show all of them. I don't think I can show all of them unless I zoom out, basically. All right, so I don't want to zoom out, so basically it's okay. It's fine. Let me zoom out a bit. Right, so this is all of them. Okay, so these are all the equations that you can actually use. Okay, so let's just have an example and then just use them in an example. All right, so in my example, what I'm going to have is I'm going to have an airplane that is flying. So of course it starts somewhere here, but I'm not going to consider that distance. And when it gets here, it launches with the velocity. All right, and then it will launch, and then so we're taking it at a time where it launches, and then maybe now the velocity is like this. It launches with the velocity v0, and that v0, let's just say, is going to be equals to 15 meters per second. All right, So if it launches with that velocity and then after some time it's somewhere here, and then v1 is going to be equals to 85 meters per second in that direction. If I tell you that it launches with the horizontal and then the angle that it launches with is 35 degrees Celsius, not degrees Celsius, sorry, 35 degrees, all right, with the horizontal. All right, so basically what is that? So which means that even here is going to have a 35-degree angle here. Okay, then I'm telling you that it takes the total time of 25 seconds to get from point A to point B. Okay, so let's draw everything and then we start considering what's happening here. All right, so I'm going to have a newer place. All right, so what's happening here is that I have an object that launches from here to here. I am told that my v0 is 15 meters per second. It's going to move in that direction. And then this is going to be v1, which is going to be 85 meters per second. And then I'm told that it covers this distance in 25 seconds. All right. Okay, so I don't know the acceleration here. I also don't know delta S. I don't know these things. So you have to find out what it is that you don't know. Let's look at the x and the y component. So I'm going to cover some distance x while I'm moving that way. I don't know that distance x. And then I do know that it's going to take 25 seconds to cover that distance x. I also don't know the acceleration in the x. I also don't know the initial speed in the x. I don't know the final speed in the x. A lot of question mark. Then going up like this, I don't know the initial velocity in the y. I don't know delta y. I don't know the acceleration in the y. Sort of things that I don't know. I do know the time that it would take to move from the y from ground to that distance, because it's moving from ground to that height. Okay, and then but then it's also moving from this position. It will be this far away in the x. So if there's a person standing here, if the person is standing here, how far, like how many meters far away in the x direction is it? It will be here, that far away. And then how high will the plane be from where they are? It will be this high, somewhere here, which is that height y. That's basically what you say. All right. So I think this is it, and then I also don't know v1y. Okay, so I don't know all of this. So I can find the acceleration though. Let me find the acceleration. I could say, well, the acceleration is just going to be v1, v0 plus a, which is the total acceleration. Then after the total acceleration, I can use the total time. And then v1 I know is 85, and then this I know is 15, plus this I don't know, and then this is 25. So basically the acceleration is going to be 85 minus 15 over 25, which is going to be 2.8 per second squared. I always forget. All right, so now I know the acceleration. So the acceleration is going to be 2.8 meters per second squared. Now I know it. Can I find delta S? Now I can find it because I know the acceleration. Now, since I know the acceleration, I can find that delta S. All right. How can I find delta S? Well, I could say v1 squared plus v0 squared plus 2a, because I know the acceleration now, delta S. So delta S would be v1 squared minus v0 squared. Because I'm using that part, the red part, that's why I can just do that. And then this is going to be 2a, which is 85 squared minus 15 squared over 2 times 2.8. Okay, and how much is that? Okay, so this is going to 1,250 meters. Okay, so that's basically the distance that will be covered and all of that. Now, I need to now consider the angle in order for me to find the x and the y components. All right, so for instance, if the question was to say what would be what would be the x component of the velocity, the x component of the initial and the final, the x component or and the y component of the initial and the final, what would be the x and the y component of the acceleration. You could find all of that. For instance, for the initial velocity, I can find the x component is going to be v0 cos of theta, which is v0 is 15 cos of 35 degrees, which is going to be equals to 12.3. Okay, and then the v0y is going to be v0 sine of theta, which is 15 meters per second sine of 35 degrees, and that is going to be equals to 8.6 meters per second. All right, how about v1x? v1x is going to be given by v1, and then that is also, if you look at it, how v1 looks like, v0 looks like this, and then there's an angle of 35 degrees. v1 also looks like that, there's an angle of 35 degrees as well. Okay, that's basically what you have. So this is going to be cos of 35 degrees. Okay, let's just say cos of theta for now, and then that is going to be 85 cos of 35 degrees, and that is going to be equals to 69.6 meters per second. And then v1y is going to be v1 sine of 35 degrees. Then this is sine of theta. I don't know why I'm eager to substitute. This is 85 sine of 35 degrees, and this is going to be 48.8 meters per second squared. If I wanted the acceleration in the x and the y, I could find it as well. I could find ax, I could find ay. Okay, so I have 2.8 at the acceleration. All right, so I could find ax. So ax would be, because remember, even the acceleration is going to be like that, and it's going to be at 35 degrees based. So this is going to be a cos of theta, which is a is 2.8 cos of 35 degrees. All right, and then we're going to find that it's 2.3 meters per second squared. That's ax, and then ay is going to be equals to a sine of theta. Remember, these sines and coses depend on your geometry. Sine of 35 degrees, and that basically becomes 1.6. All right, so now basically I have almost everything that I want. So if, for instance, if they were to say to you, find that delta x, what would be delta x, for instance, you could find it. So let me just lower everything. Let me say, for instance, they said to you, find what delta x is going to be. All right, so now you have the accelerations and you have everything. You could find delta x. So if you wanted to find delta x, what you could say is, you could say, well, my delta x, if you want, you could do it like this, going to be v0x in the x direction, and then this is going to be the time that it would take to get there, plus, and then you say half the acceleration, the x direction, and the time squared. So this would be the s component of the velocity is 12.3, so you have to be careful. 12.3, the time would be 25 seconds, and then this would be half, and then the s component would be 2.3, so you have to be careful, and then this would be 25 squared. And then how much will that be? Okay, so this is going to be 1026.3 meters. You could find delta y as well if you want. Let's just find delta y differently, just so I can show you can use different equations. So since I know the initial and the final velocity, because I know all the components, I'm going to say this is going to be the final velocity of the y component and the initial velocity of the y component plus 2ay and then delta y. So which means that my delta y is going to be equals to the final velocity of the y component minus the initial velocity of the y component. Then take everything up and squared, and then this is going to be 2 times the y component. All right, so what is that? The final velocity of the y component is 48.8 squared minus the initial is going to be 8.6 squared, and then divided by 2 times 1.6. All right, and then my delta y in the y is going to be equals to, okay, this becomes 721 meters. You could also check if this is true. I mean, you already found that delta x is 1.25. So if you take the square root of 1026 squared plus 721 squared, you do get 1254. So the rounding off is the one that is basically affecting it. So that is fine. More or less, you are getting the same number. So that is okay. All right. So basically, this is how you can approach the equations of motion in 2 dimensions. I know it can be a little bit tricky, and you have to be very sharp and actually track everything, and that can be a problem sometimes. It just depends on the day as well. Sometimes it can depend on the day, to be honest. All right, so but then you must make sure that you are very careful, and you understand what are you tracking and how it works. All right, so let's just do the last section on these ones, which is projectile motion. Remember, 1 dimension we had free fall, whereby something was going up, something was going down, and now we are doing free fall in 2 dimensions. All right, so we are going to do free fall in 2 dimensions. Remember, free fall, what we're doing is we ignore air resistance. So the only thing that is affecting us is the acceleration due to gravity. That's basically the only thing that is affecting us. All right, so that's accelerated. That's your free fall. Right, so how does it look like? Now remember, in 1D you were launching something up, and then it will go up, reach the maximum, and then afterwards it will come down and basically come back to the same position. So it will go up, come down the same line, okay, and hit the same position that it left. Okay, so basically that's what you have in 1 dimension. All right, so in 2D, what is happening is that you are launching a projectile, whatever object is, but at an angle. So meaning that there's going to be an angle here. So you have a speed v0, but at an angle theta here. All right, now remember what's going to happen. Remember, you have this going down. This is the acceleration is only going downwards. So what's going to happen is that your object is going to move like this, but because it is being pushed down by the acceleration, it is going to slow down in the y direction. In the x direction, nothing is happening, and then it slows down eventually somewhere, and then it's going to come back, come back, come back, come back, and then it's going to hit the ground again. Now it's going to hit the ground with a velocity v. So if here at maximum something is going to happen, when your ball is here at maximum, the y direction, because if you look at it, if you just look at the upward motion, it is slowing down. It is basically living with the velocity, some velocity, and that velocity is going to be the y component. And then it is going to stop. So this v1 is going to be 0, v1y is going to be 0 meters per second. Then it comes back down, and then it comes back down, and then it hits the ground again with velocity v2 in the y. All right, now because there's acceleration in the y, so it is slowing down. All of this is affected by this minus 9.8 as the acceleration. So it is slowing down in the y. So it means that when it's here, right, I have to first break it down. So if we look at my v0, my v0 is, there's my v0. So I need to find out what is v0x, and there's going to be v0y. Okay, and then there's going to be theta here, which is this 35. So you can actually see that since the acceleration is only in the y, there's ay, and ay is in the minus 9.8. Okay, that's ay. But there's no acceleration in the x. In the x direction, the acceleration is 0. Because there's no wind, there's nothing that is pushing it in the x direction. Okay, there's no acceleration, there's no force in the x direction. So the only thing that is making it move in the x direction is because it has this x component of the initial velocity, and that is why it is somehow moving that way, but then the gravity is also slowing it down, all right, as it goes up and then makes it faster when it comes down. All right, so you end up with a situation where it's like this. So when it's here, right, your velocity vector, your velocity vector is not that much, it's lower now, it's smaller, which means that your x is still the same size, but your y is very small now. Your y keeps decreasing. When you're here, all of your speed is just facing that way, which is your v0x, because your v0x is actually constant because there's no acceleration in the x direction. All right, so hopefully you understand. Let me just break it down what's happening. All right, so you have a situation whereby you launch the ball in this direction, so your ball is going to go like that, going to come back up. All right, roughly it's supposed to be parabolic. So let's see what happens in the y. Right, you guys would say, agree with me, that in the y I do have the acceleration in the y, and that acceleration is gravity, which is minus 9.8 meters per second squared. I have that acceleration. So which means that since I'm launching this ball with a velocity of v0, it has a v0x component, then it has a v0y component. Okay, so it has some velocity in the y. So if I just look at the y and I'm launching it here, it's going to leave with a v0y in the y direction. That's basically the speed. But if it does that and there's acceleration going down, it's going to slow down such that at some point here, v1y is going to be 0 meters per second squared. Sorry, not second squared. All right, just second. Basically, that's what you're going to have. All right, then when it reaches that point, which is now it is at this point here, what happens? It starts coming down. So it's going to start coming down. So it's going to leave this point v1y at 0 meters per second in the y direction. And then it's going to hit here with v2 in the y direction. I don't know that v2, but then if it's hitting at the same position as this v2y is going to be minus v0y. It's going to have the same magnitude as the y component of the velocity. All right, so if for instance my angle theta here with the horizontal, so when it comes back it's going to hit, and then it must still have the same angle here with the horizontal. All right, so these two angles are going to be the same basically, but you could call this v0, and then you could call this v3, in this case v2, sorry, and then you could call this v1, because these are the most important points during this motion. All right, so this is what is happening in the y. What is happening in the x? Well, in the x, ax is 0, there's no wind, there's nothing, so there's no force that is being applied on the object in the x. So in the x, it has an x component, so it's going to leave with a velocity in that direction, which is v0x. When it's here at maximum, somewhere here, it is still having v0x. When it hits the ground, it is still having v0x. So which means that v0x is just constant. It's not changing because the acceleration is 0 in the x direction. So v0x is not changing. Okay, so this is how you can break it down. So when you write it in terms of equations, this is how you can write it in terms of equations. Okay, so I'm going to have, there it is, and then it's leaving at theta. There's my v0. So it's going to go, Power Rangers. All right, and then after that, it's going to have v1 here. v2, sorry, I'm going to call it v2, and then there's your maximum point, which is v1 here, which is the y component is going to be 0. So v1 is not 0, but the y component is 0. So let's just assume that this is the ground. So this is true if it's hitting the ground. And then the velocities are going to be the same. V2 and V0, the magnitudes are going to be the same, but the directions are going to be opposite one another. Basically, that's what it has. They're going to be in not opposite one another, but they're going to have different directions. All right. So the question now is, how do the equations of motions look like? Well, let's look at what happens in the y. What happens in the y, right? I do cover some y distance. I mean, you can tell I do cover some y distance, and that y distance is here, and then I cover it. So I do change my y. So my y is changing all the time, and my x also is changing. There's my x. So my x is also changing all the time. At some point when I'm here, my x is this, my y is that. When I'm here, my x is this, my y is that. When I'm here, my x is this somewhere in between, and then my y is that. When I'm here, somewhere here, my y is that. When I'm here, my x is this one, so meaning that the x has covered all these things that's up to here, and my y is here. When I'm here, my x is here, but my y is 0. So I am changing y with time. I am also changing x with time, and also y is changing with x basically, right? But we'll come back to that one later. Okay, so I could actually consider distance in the y, and I do have the acceleration in the y is minus 9.8 meters per second squared, so which means that I do have acceleration in the y. So how do the equations look like? I could say v1 y, whatever final velocity, just depends on what final velocity. So I'll just say final y is going to be initial y plus the acceleration in the y direction over the time. Now the time is the same, right? Whatever y was covered, x was covered as well. So while you're covering y, you're covering x. So it's still two dimensions, still similar to the example of the plane that I explained above. The only difference is the trajectory is different, right? Then you could also use this one and say v final velocity of the y squared over the initial, all right, let's call it initial, on the y squared plus 2 ay delta y. So y is going to change, it just depends. All right, you could also use this equation that says I could find delta y. My delta y will be given by the initial velocity in the y direction multiplied by the time that it took for the motion or whatever interval I'm considering, and then plus half ay delta t squared. Okay, you could also use this equation. Okay, so you could also use this equation that says delta y is going to be given by half the final velocity in the y direction and the initial velocity in the y direction, okay, multiplied by time. So you could also do something like that. What about the x now? What about the x? Well, in the x direction, first of all, my acceleration is 0 meters per second squared. So I don't have acceleration. So I can't use all of these equations. The only equation I can use is the one that says delta x is going to be equals to half. I'm going to simplify it. V0, this one I can use, just going to be V0 x plus the final velocity is also going to be V0 x, because I said that it doesn't change in the x direction over change in time. So basically the equation that you can use is delta x is going to be V0 x multiplied by time. This is the equation that you should actually use all the time. So this is the only equation that you can use in the x direction. That's it. That's the only equation. So the only tricky part here is the y direction. The y direction, things are changing, and then you have to consider what's happening. All right. So this is good. Now let us just consider other things as well. All right. So now I'm going to do a lot of maths. Okay. I'm going to do not a lot, but just some maths basically. So I have it like this, and then I have my theta here. There's my v0, and then it'll come back, will hit somewhere here, so go blah 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 blah, and then it's going to hit somewhere here, and this is my theta. All right, and then this is my v1. Okay, all right. Now the question is, what's going to be what's going to be set different number of things. I'm going to track what happens if, for instance, I draw an x and a y Cartesian plane here. How can I actually simplify it if I call this x and I call this y? So you can see that it's changing with y and it's changing with x. So I want to know if it's possible for me to find something like that we call the range. So the range would be from here, you go all the way to here. That is going to be a range. You're going to call it delta r, and that's the distance that is going to be delta x, basically, of your final point, like from where you started in the x direction to where you ended. That's basically going to be your range. Okay, so in this case, this is, I'm just considering this case. If this case changes, things change. All right, and then I'll tell you what changes. Then how is it going to vary with the y? All right, so let's look at the equations now. First of all, if I want v0x, can find it, I can just say, if I know v0, this is going to be cos of theta. Let me make it thicker. All right, and then if I want v0y, this is going to be v0 sine of y of theta. Why? Because v0 is like this. This is x, this is theta. We've done this since we started this section, and then this is v0y. So you have to make sure that you track it. All right, now let's look at the equations. I have this equation that says that my delta y is going to change. It's going to be v0x multiplied by time plus half the acceleration in the y, okay, the acceleration in the y, and then multiplied by time, right? But I also have this one that says that my x is going to be equals to v0x, v0y, not v0x, sorry, over delta time. So I can actually find that my delta time is going to be equals to delta x over v0x. All right, so if I do that, I could do something. All right, so this is more like my equation 1, and then this is more like my equation 2. I could substitute whatever time. So I see time here on equation 1, I can put that. So I see time, I just put that. So when I do that, it becomes delta y is equals to v0y. Now when I see time, I'll have delta x over v0x, and then plus half ay, and then where I see delta t, I'm going to put delta x, and then v0x, but then here everything is squared. So what I'm going to do, I'm going to change delta y to become y. I am also going to change delta x to become x. When you do that, because in reality that's basically what is happening, you could track it like that. So this is y is going to be equals to v0y. I'll take this one, divide it here, then this becomes v0x, and then that becomes x. Where I see x, it becomes x, and then plus all right, okay, it's fine, I'll change later, over that half, and then ay, and then this becomes x squared over v0x squared. That's basically how it becomes. Then where I see ay, I'm going to put minus 9.8. Then I'm going to write everything. Okay, let me not confuse you. So this becomes y, right? v0y, v0x in the x. And then I am going to have plus half. I don't want to confuse you. Minus 9.8. All right, and then this is going to be x squared over v0 x squared. Now I can rearrange this whole equation. How does it look like? It looks like this. All right, so you could actually just put it as minus g. You could do it like that as well. Just put it minus g. Instead of putting that, actually let's just put it as minus g instead of saying 9.8. So what I could do is I just say minus g. instead of putting the number. So let's just say minus g like this. All right. It's going to help us when you say so, which means that when you see g now, you're going to put 9.8. Remember, g is going to be equals to 9.8 meters per second. G is just the magnitude of acceleration. Rearranging this, what I get is I get that g minus g over v0x squared, right, over 2 that, and then x squared plus v0 y over v0x over x is going to be equals to y. Now this equation here is like a parabola. I'm just going to show you examples. All right, so this is like a parabola, but then this is a parabola that is going downwards. Remember, if I say y is equals to x squared in mathematics, I draw a parabola like this that crosses the line at 0. If I say y is equals to minus x squared, I draw a parabola, but that is facing downwards. So there's a minus here before the x squared, so this is going to be a parabola that is facing down. All right. Now, if I say y is equals to x squared, let me say plus 4. So what I draw is a parabola that is going to cross at 4. Right? It's going to intersect at 4. It's going to turn at 4. If I say y is going to be minus x squared plus 4, what's going to happen is I'm going to have a parabola that is going to intercept at 4, but is facing downwards. So there it is at 4, intersects at 4. So if I have like y maybe is equals to like x squared plus 2x, and then if I just maybe put it like this. All right, so this one basically you shifted your parabola, and then so it's going to turn somewhere 2. For instance, when it's 0, it's going to be 0. So you have a situation whereby your parabola is going to turn somewhere here. So basically, I've shifted it. All right. So if you put a like a plus 4, if you put like a plus 4, for instance, then basically you shifted it maybe to the left, but also it's still facing up because it's positive here, right? Still facing up, and then you've shifted it to the left, but also you are going to intercept it upwards. All right, that's basically what is going to happen. So if you put a 4, for instance, there. All right, so I'm not teaching you guys maths, but I'm just showing you that this you can actually see that this is actually the same as it maths. All right, so I just basically remove that. Okay, so now what you could do is, if I put a minus, for instance, if I put a minus here, how would it look like? If I put a minus, let me just draw it using that one. If I put a minus like this, okay, so if I put a minus there, what's going to happen is that it's going to be a parabola that is going downwards. All right, and then what's going to happen is that this parabola also is going to shift. Okay, so at 0 is still going to be 0, yeah, and then somewhere that's where basically it's going to turn. So you have a parabola that basically looks like that, and so you can see that this is a parabola as well that looks like that. Now let's consider our motion. All right, so let me just write it side by side. So I'm going to have this y, there's this y, there's this equal sign, the negative, there's the negative from here, and then so you could have an equation like this. Maybe let's say this minus 3x squared plus 2x. So this could be anything. I mean, this could be constant, and then it will still more or less look like that. It's still going to intercept at 0, and then it's just going to shift differently. It's not. So what you do have is you have this value here. These are constant. This is 9.8, and then this is going to be a value. So this is constant. It could as well be 2, 3, 4, 4.1, whatever. Right, so this value here is a constant. This g to vox is a constant, so it could be something like a 3. All right, just don't think about this one now. Look at this one below. All right, then there's my x squared, then there's my x squared. I don't know why I'm doing that. So x squared, and then this is going to be plus voy vox x. So this also is a constant. I mean, this is a constant. It could be, maybe just think of this like it could be 3. Think of it as it could be 2. Then there's your x squared, there's your x, So it looks more or less like this, the format. I'm not saying this is definitely going to be 3 all the time, this is going to be 2 all the time. I'm just giving you an example. I'm saying it just looks like that. So you can actually see that in actual fact, when you are throwing an object, launching it at a different angle, all right, theta, let me say this is theta, you are going to have a situation whereby it's going to form a parabola, all right, so which is just this part here. So it's going to go like this, then forms a parabola like that. Okay, so it behaves exactly like a parabola. All right, now let's take this up a notch and find the range. We are going to find the range. I'm going to summarize everything at the end, and then I'm going to do an example. I'm going to find the range, and then also I'm going to summarize this equation of y here. All right, so let's summarize it further. Remember what I said? I said VOX is going to be VO, right? Said it's going to be VO cos of theta. And then it said VOY is going to be VO sine of theta. So what does this mean? So I have an equation that says this minus G 2 VOX squared, right? Everything is going to be x squared plus VOY VOX x not squared, just x. Okay, so I could say this is minus G, and then this is 2. Where I say VOX squared, I could say it's VO sine squared, and then this is x squared. This is plus VO cos, sorry, VO sine of theta. This is going to be theta, I forgot theta here, over VO cos of theta over x, not squared. I don't know why I keep doing squared. All right, so my y could be simplified as minus G. Let me take it out, make some space. So it could be minus G 2 VO squared sine squared theta. All right, so you could write it like this over x. So if you just know the angle and you just know the initial velocity, you could actually track how everything is going to change with y. And then this is going to be plus, the VO is going to cancel, and then this one sine theta over cos theta is the same as tan of theta x. So you could actually write your equation either like this one on top, or you could write it like this one below. Right, so it just depends on the information that you already have, and then you could just work it out like that. So you could write your equation like this. So you could find everything, the height, how far is it, if provided that you know what is x at that point in time, and all of that information. So you could actually find it like this. Okay, so this is what you could actually use. All right, so how about the range? So let's think about the range. The range is basically this distance x here. It goes from here to here. It's how far it will travel before hitting the ground again. So let's think about the x. So I want to find out, so I'm just going to say delta x is going to be v0x, right? Remember I said that this is v0x over time, right? And remember we said that delta y is going to be equals to v0y, okay? There's v0y, and then delta time, and then there's going to be a minus here because I put a minus there, and then a half g delta time squared, right? This is basically the equation that you're going to have. All right, so if you look at delta y, it starts here on the ground, comes back, hits on the ground. So y0 is 0, y2, because this is y1, y2 is also 0, so which means that delta y is going to be 0 minus 0, which is 0, because delta y is going to be y2 minus y0, which is 0, minus 0, which is 0. So this one is going to be 0. So this is 0 equals to v0y delta t minus half g delta t squared. So if you take this negative one this side, what you have is you have half g t squared, which is going to be equals to v0y t. So basically if you solve this, it means that your t is going to be equals to, I'm just solving for t, it's going to cancel 1 here, it's going to be t voy divided by g, right? So where I say t, if I call this equation 1, I'm sorry I'm doing a lot of maths now, and I sort of promised that I won't do so much maths, but this one is anyways for university students, so they should be able to follow what I'm doing here. All right, so I'm just going to substitute whatever I have on equation 2 on equation 1. Therefore, my delta x, right, which is the range, because if I'm calculating it from y0 to y2, delta x is the same as the range, and that range is going to be equals to v0x delta t. So let me substitute. So this range is going to be v0x. Where I see delta t, I'm going to put 2 v0y over g. Okay, so if I do that, this becomes, where I see this, it becomes 2 v0x v0y over g. This is the same as 2 v0 cos of theta v0 sine of theta over g, right? That's my range. So what happens here, basically my range becomes 2 v0 squared. Now sine theta cos theta, this 2 sine theta cos theta, let me write it in such a way that you will recognize it. So let me just write it and then make space and write it again. So I will write everything again. So this is r is, I'll say v0 squared, and then this is going to be 2, let's just say sine theta cos of theta, it's the same. All right, and then everything is going to be divided by g. But this value here, it's a trigonometric identity, which is basically sine 2 theta. All right, so which means that my r is basically v0 squared sine 2 theta over g. So if I know my initial velocity and I know my gravity, I can actually find, and I know my angle, I can actually find the range. Okay, now this is true only if you launch a ball at some level, it comes and lands at that level, then that is true, you can actually use this equation here. That equation is actually true if that is the case. But let me say, for instance, you have a ball that starts here and then it goes and then it lands somewhere here. Then you can't use this equation. You can't use it. This equation is only true for this case. If you have this case, then you can't use that equation. You can't. You can only use it if this is the case. All right. If you have case number 2 here, then you have to know some information, and then the problem is different now. All right, so this is very important. You can only use this equation of the range if this is the case. Then you can use it, because we derived it for that case whereby delta y0 is 0. If delta y is not 0, you can't use this equation because you're not going to get this. All right, so please do me that favor and understand what is happening. All right, so I know that this is a lot of stuff, just put a lot of information and it's starting to be confusing for you guys. All right, so what I'm going to do is I'm going to summarize everything into one space, and then afterwards I'm just going to do an example. We're going to look for maximum height, we're going to look for the range, and then we're just going to look maybe for something else. We'll see what to do. All right, so let's just see what we're going to do. We're going to have this one, and then it's going to land somewhere here, and then blah 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 blah, and then there it is, and then we said that it's going to land somewhere here. So it launches with, I know I didn't draw it very well, it launches at some angle. Okay, maybe let me just draw it very well. Okay, let me just draw it very well. So I'm launching it at some angle, and that angle is theta, and that is v0. And then what we said was it is going to go like this, going to go like that, then it's going to drop like that. Just think of it like it's a parabola. I know I didn't draw it very well. So here is going to be the maximum point. All right, let's call that maximum point v1. I don't know v1, but I do know v1y, which is 0 meters per second. I don't know v1x. That's very important. Then here it's going to hit with the velocity. That velocity will have an angle theta there. Let's call that velocity v2. I don't know it. So what do I know? I can find v0x is v0 cos of theta, and find v0y is v0 sine of theta. That's so I can do that. I can find those two. Then what else do I know? I can use the equations of motions, and then I can check y. Y is going to be equals to minus g over 2 v0, I think is v0y, all right, squared, and then x squared, you could put this in brackets if you want. Then this is going to be plus v y v 0x in the x direction, and not in the x direction, multiplied by x. This is a parabola. This equation is said that it can be simplified. It basically becomes minus g over 2 v0 squared, and then we said this is going to be sine squared theta, and then x squared, so you could have it like that, and then we said this is going to be plus, and then we said this is going to be equals to tan theta. You could put an x here if you want, x tan theta. Right, so you could use these equations, and then we said that the range is going to be equals to v0 squared and then sine 2 theta then over g. All right, so this is very important. These are the important equations basically when you are dealing with equations of motions, right? So it allows you to track everything, and then you can actually just work out everything. Otherwise, you can just use on your x, you can just say delta x is going to be v0 x multiplied by time. You could use these equations that says v final, so it just depends on the interval. So v final at 1 is going to be v initial at y plus a at y delta t. You could use v final at y squared, v initial at y squared plus 2 ay, whatever a is, and then delta y. You could use that as well. All right, these are the equations that you could use, and then the additional ones that you could use. All right, just to put a correction here, this is not, it's not sine, it's supposed to be cos here. I made a mistake here, sorry about that. This is supposed to be cos, so this is going to be cos, not sine. So, and then when I go down, I just nearly made that mistake. Okay, so when I go down here, this is not going to be v0y, it's going to be v0x, which is cos squared theta, cos not sine, squared theta. Maybe let me write it neatly. This is v0x, this is fine, and then this is just going to be cos squared theta. All right, everything else should be fine then. All right, so I think this is fine. And then I'll just highlight certain things and before I do an example. Okay, and then here I'm going to have delta y. Here I'm going to have delta y. It could be half, and then whatever the final velocity is, final velocity in the y, depending on the interval, initial velocity in the y, delta t basically. Right, so you could use all of these equations. You could also say delta y is v0y, delta t, and then plus half ay, and then this is just delta t squared. And remember, ay is just the same as minus g. So you see ay, you could just substitute minus g. Then of course they are going to look a little bit different. You just put minus g, minus g, minus g. You can rewrite them. All right, so you could actually do it like this. So these are all the equations, these are correct. Don't forget guys, I made a mistake when I was deriving this equation. I've already fixed it. Just make sure that you take note of that. Here I had sine, so it was supposed to be cos squared. I just saw it when I was thinking about this one. All right, and then otherwise every equation should be fine, should be correct. Okay, let me just go. I'll just check offline and just check if I didn't make any mistakes. All right, so just a couple of things now to note. For instance, if I launch the ball at different angles, so I just want to compare how the range is going to be. So for instance, if I launch it at, let's just say there's my ball, I launch it at 30 degrees, right? So if I launch it at 30 degrees, it's going to travel long. Okay, maybe it's going to land here. Now the question is, what happens if I launch it maybe like 60 degrees? Maybe I launch it at 60 degrees, there's 60 degrees. So now the blue one is 60 degrees. I'm launching at 60 degrees. Okay, so when I launch it at 60 degrees, it is going to travel a higher height, and then the range is going to be a little bit shorter. All right, so you don't expect the same ranges. This is the range when it's 60 degrees, and then this is the range when it is 30 degrees. So you can see that when I change my angle, even the height changes. I mean, look at the height here. This is h here, and then but then if you look at the height here is long. So when you change the angle, you get a higher height, and then but then a shorter range. And then when you change when your angle is smaller, you get a longer range and then a very smaller height. All right, so this is the effect that you must also take into account and think of, and just be aware of. All right, let's just do an example. I know this section is a little bit confusing to some students, but just try and go through, just go over it over and over again, and then maybe you can understand it. If you still can't understand it, just tell me in your comment sections, and then maybe I'll try and find time, and when I do get time, I'll just do a video if I'm just explaining it maybe in a different way that maybe it will make sense to you. All right. So otherwise, let's just do some example. Let's just have a ball. We're just going to launch it at 30 meters per second. I like 30 meters per second for, I don't know why. Let's keep 35 degrees. All right. So what we want here is we want the height that the ball is going to travel. We want the range that the ball is going to travel. And also maybe let's just find the final speed. That would be interesting. So we're going to find the final speed. We're just going to find the height that the ball is going to cover. We also going to find the final speed. All right, let's call it v2. So we're going to call this v1. I don't know v1. And then let's also call, but I do know v1. All right. Well, I put calculated, let's put it like that. And then here we're going to find v2. So let's find v1, let's find v2, and then let's find the height, and let's find the range. Okay, so let me try. I think it's going to be off screen. Let me try and bring it on screen, everything. All right, so we want to find v1, we want to find v2, we want to find the height, the range, and that's it. All right, so the first thing I think that is going to help us, let's just find v0x, which is going to be v0 cos of 35. That is 30 cos of 35 degrees, and that is going to be equals to 30 cos of 35 degrees, which is 24.6 meters per second. V0y is going to be 30 sine of 35 degrees, and that is 17.2. I think we had some example like this. I think numbers sound similar. All right, so now what we want is we want the velocity here, v1. All right, let's just say we want v1. Now let's look at v1. What is v1? We know that v1y is going to be equals to 0 meters per second. And so which means that here, all of the velocity is just going to be pointing in the x direction. And we know now, because we have found that v0x is going to be equals to 24.6. And we know that v1x is going to be the same as v0x because it's constant. Remember, in the x direction, the acceleration is constant. So which means that it's just going to be constant between that whole distance. So at v0, we're going to have v0x. At v1 is v1x. At v2 is v2x. But all of them are the same. I mean, this is going to be the same as v0x. This is going to be the same as v0x because it's constant. right? So which means that my v1 is going to be v1x plus v0x, but v1x is the same as v0x, and then this is, sorry, v1y, right? Then my v1y is 0, so this is just v1 is going to be the same as v0x, which is going to be 24.6 in the x direction. That's basically my v1 vector. All right, so that's my v1 vector. All right, so that's v1. The magnitude is going to be 24.6. And then how about the height? Let's find the height. Well, I could find the height. I could just use the y because I know information on the y. So what I could do to find the height, I don't have the time, so I could say, well, v1y squared is going to be v0y squared, because I know the initial velocity in the y direction, then the final velocity in the y direction, plus my 2ay, right, delta y, which is going to be the height. I mean, you could call this delta y if you want. Okay, the height, you could call it that. All right, so basically this means that I can actually find my delta y. My delta y is going to be v1y squared minus v0y squared divided by 2ay. So this is v1y squared is going to be 0 squared minus 17.2 squared divided by 2 minus 9.8, because remember ay is minus 9.8. You always have your ay facing downwards, and that is 9.8 meters per second squared. Okay, so when you do that, you'll find out what is ay. Okay, so it's going to be 15.1 meters. Right, so the ball is just going to reach 15.1 meters if you launch it at that angle. All right, and then what else do we want? We want v2 and then the range as well. Okay, let's find v2. So let's look at v2. So we expect v2 to be something like this. There's going to be v2. What we do know is that this direction, this v2x is going to be the same as v0x. All right, so whatever the angle that I have here, it must be able to give me v0x, basically, right? It must be such that when I do v2, I should get v0x. All right, and then also I am going to have the final velocity, which is going to be v2y here as well. And then both of them, they are actually going to give me what is going to be v0x. Okay, so I could find the y. The reason why I'm thinking it might be easier to find the y is because I already know the height, right? I already know the height moving from up to down. So my delta y for that one is going to be minus because it's going down 15.1. I already know the acceleration, so I could actually find out what is going to be my y component of that. I already know the x component of that, and then I can actually find out what is going to be my v2, and I can also find out what is going to be my angle. Okay, just to verify if the angle is going to be the same as that, you can just find out if that is the case. Okay, so my height, so basically I have that, so I could use the height, and I know the height, I know the initial velocity, I want the final velocity. So what I could do, I could say v2y squared is v1, the initial point is going to be 1 because I'm taking it from maximum. I don't know where to sketch it. I'm taking it, remember the ball is like this, so I'm taking it from this point, point 1 to point 2. So v1, v2, I'm using that interval. Okay, so v1y is going to be that, and then plus 2ay, which doesn't change, and then that ay. Now remember, now my ay is going down, so it's going to be negative. So I don't know that. I'm just going to put the square root. So this is going to be 0 squared plus 2 minus 9.8 minus 15.1. Okay, this becomes the square root of 2 multiplied by 9.8. All right, so it turns out this is 17.2 That's basically what I get. It turns out that it's going to be 17.2 going upwards, which makes sense because whatever velocity going down is going to be the velocity going up. All right, so that's my V2 Y. All right, 17.2 meters per second. I already know what is my velocity Vx. So I know that my velocity V2 is going to be given by V2x plus V2y. But I know that my V2x is going to be the same as my V0x because it's constant. And then this is going to be V2y, which I just calculated now. All right. So when I substitute this one, then my V2 basically becomes 40 something. Or is it 40 what? 20, no? Oh yeah, 24. 24.6 in the x direction plus 17.2 in the y direction. All right. I already know what's going to be this one. So if you just do the magnitude, you're going to find that this is going to be 30 meters per second. So let's just do that. I don't know why I did do that. 24.6 in the x direction plus 17.2 in the y direction. I don't know why it erased. Okay, so if you do the square root of that and you say square root of 24.6 squared plus 17.2 squared, you're roughly going to get 30. Roughly about 30. All right, now I have two of them. So this is just, I don't know why it's doing that. All right. So basically roughly is going to be 30 meters per second. So you can see that because they are going to land at the same level, so whatever the speed v0 was, it's going to be the final speed, just different direction of v2. All right, so this is true. I mean, so this is true even in the case of 2 dimension. It was true in the case of 1 dimension. All right, so this is fine. What else do I need? I need a range. So the range is fine. Remember what I said, the range, you can find the range using this equation. So we said we can find the range using, since it's landing on this, on the way it started, we can use this equation that basically says v0 squared sine 2 theta, right? And then over g. So that basically becomes 30 squared sine, and then we say 2 times whatever the angle, which is 35, and then this becomes g, which is 9.8. Don't put minus, put 9.8. Put 9.8 here. Don't put the minus because you already took care of the minus when you were deriving this equation. All right, so this becomes r, basically becomes something like 30 squared sine of 70. All right, and then this is going to be 9.8. So this becomes 30 squared sine of 70 and squared sine of 70, 9.8. This is 86.2. So this is going to be 86.3 meters per second. All right, so that is my range. You could also check this one if it's correct. All right, so you could check it also if you just break it down and say 2 cos of theta sine of theta if you're not sure, but then this should give you the same answer anyway. Not meters per second, guys. Sorry about that. Just meters. It's going to be meters. All right, so basically, guys, I think this is it on this section. I know it was long, it was a little bit confusing when you get to projectile, and generally, to be honest, lecturers like doing projectile questions because it gives you so many options, and basically you can challenge students in different ways. So this section is a bit challenging and can be very challenging for students as well. So what I would ask is that please practice this one. Get textbooks, different textbooks depending on your university. Check different examples. Just practice and practice and practice and practice and practice. All right. Otherwise, from my side, guys, this is it. I'll see you guys whenever I go through the next session. And then, all right, cheers.